Welcome today to another one of James M. Pleasance's design seminars. This particular one is from our plumbing water system program, which is an all-day program. And we would like today to focus in on domestic hot water recirculation. It's a subject that we find people don't really think about that much, and they take it kind of for granted. And I would have to admit, most of the time it's not a major issue. However, there are specific things that you need to slow down and think about to stay out of trouble. So the purpose today is kind of educate you on why we do domestic hot water recirc and where you might slow down a little bit in your design process and make sure that you stay out of trouble, because there are some issues there that you need to be aware of. So first of all, trying to get you focused in on what we're talking about. Here's kind of a picture, and this, by the way, is condensing water heaters, which you might note the cold water line is coming over and going into the water heater first, where on non-condensing water heaters, we bring the cold water makeup into the storage tank first. Simple little change, but kind of be aware of that, and we'll talk about things like that a little bit, try to help you out. Let's look at little red recirc pumps. You see that building return recirc pump? We want to focus in on that particular application, purpose of which obviously is to keep the water warm out close to the showers, close to the fixtures, so when you go to use them, you don't waste a lot of water. There's another recirc pump that's referred to in the codes. It's this constant flow pump between the water heater and the tank. And there's some energy requirements on that particular pump in the code, which we'll show to you as we go. So we want to focus on plumbing, domestic water, why and where you need domestic hot water recirculation pumps. So why? Why would you even bother adding all these pumps to systems? I think we got to slow down a little bit and realize water usage. And this slide is dated for 2000, but I think the point is very well made. In the USA, we use an awful lot of water. In the Southeast, we probably average about 180 gallons of water per person. Now, that's what your personal private use is in your home. That would be showers, dishwashers, cooking, whatever you use in your home averages that kind of water usage. One of my favorite little comments is this egg thing that kind of blows people's mind, but it takes 120 gallons to produce an egg, and that's from the time that you have an egg and you hatch it to a little chicken and you grow it up and you feed it up big enough to have eggs, divided out by the number of eggs that chicken will produce in its lifetime and the total amount of water. So pretty interesting little stat there, about 120 gallons per egg, but I think the point's well made, and I think you kind of have the message. So we're talking about water. Those of us in the Southeast have been blessed, but we can go back to Georgia area just a few years ago, and they had a serious drought. If you get over to Vegas anytime soon, notice the big white ring around the top of Lake Mead. The Southwest and California is in a serious water shortage now, and it's going to get worse. And we want to focus on how to save that water, so you understand why this recirc pump has become part of codes. The whole surface of the earth is, lots of water, but unfortunately it's predominantly salt. And the other key thing you need to look at is the population. That world population is growing rapidly, and if we look at the total numbers as it grows, obviously we got to have more fresh water. And we are already in trouble, so as we grow, you're beginning to see we've got to pay attention to this resource. Water is a precious resource. We're just going to have to manage better in the future. So what is the purpose of hot water recirculation and hot water recirculation pumps? Very simple, to save water, to conserve water by providing hot water to the fixture quickly. In other words, you get ready to take a shower. Nobody likes to take cold showers, so you get in the shower. How long does it take the water to get to the shower? The hot water, and all that cold water is going where? Down the drain. You're washing dishes, whatever you may be doing. You really want your hot water to be there pretty much instantaneously. And all of us, including me, will sit there and wait until we get that hot water. And what we're trying to do with the recirc concept is to save that water, conserve that water. Don't throw it down the drain. Let's use it. And that's kind of a simple way to get this conversation started. Here is a snapshot from Energy Code 90.1 2010, which is becoming the building energy code throughout the country, and will be shortly. If it's not in your state, it will be there shortly. couple little quick comments on surface water heating I think kind of interesting. And surface water heating is what we're talking about. Temperature maintenance, and then red might be important the way I teach. Automatic time switches and other controls. Those you shall have a timer and actually temperature sensing controls so that when you're not using hot water, like late at night, you have the ability to program the pump and turn the pump off. So the energy code is saying, let's turn these pumps off when we don't need them. If we can program them, we'll have temperature controls, let's kill them energy-wise. Next statement is they say, let's hold the maximum temperature to 110 degrees. And most of us have been in the business, we probably would say about a 105 to the actual fixture is okay. 110 probably okay, but limit it to 110. Last but not least, this is circulating pump control at the bottom, and that's the one that circulates the water to the tank and the water heater. This is not the recirc pump all the way out. This is the pump that moves the water between the water heater and the storage tank. And basically it's saying after 5 minutes of the water heater turning off, we got to kill the pump. And the reason it's running this extra 5 minutes is to take any residual heat out of the water heater when you turn it off and put it in the storage tanks. That's a whole lot more efficient than leaving the heat over there and not doing anything with it. But why continue running the pump once it's pulled the residual heat out? Pretty basic, pretty simple stuff. But here's the message from 90.1 2010 Energy Code. Cycle the pump, turn it off. And I think you need to keep that in mind when you look at the next slide. This is OSHA. What's OSHA say? It just kind of got you in a box. I think the most important thing that get from this particular slide is OSHA is worried about Legionella, and we know it can thrive in hot water systems. They don't want any dead legs or any areas you don't have recirculation through. Down under maintenance, section 3, they want you to get that water to roughly 140 degrees to kill it. And last but not least, the domestic hot water recirculation pump shall run continuously. And that's directly in violation with the energy code. And as you say, they're claiming that the recirculation hot water pump should be excluded from the energy conservation measures. It's kind of important. A lot of you engineers probably never seen these two things. Which one are you going to design to? I'm not trying to pick on you. I'm just trying to see the box you're in here. Energy code says cut it on and off. OSHA says no, run it continuously. You got to make your choice. I think most people are going to go with OSHA. I got some good news coming for you, not quite here yet, but make sure you understand that in a minute with the Legionella thing. The Legionella thing is still growing, and here's a little snapshot from a newspaper back 2012. But there's a lot of cases of it out there, and just to remind you, Legionella is connected directly with pneumonia. So this shows a death, but most people who contact this do not die, but they do get pneumonia from the Legionella bacteria. So the point is we need to be aware of that. So as you move forward working with water, you're going to have to kind of keep some of those things in mind. We'll come back to that subject in a few slides and give you a little update on some new standards that are coming. Let's look at domestic hot water recirc pumps. Why they're there is to save water. What are the important things you need to know from a design standpoint to use and apply these pumps? Number one, we're trying to offset the supply insulated pipe, hot water heating pipe heat loss to some delta T. In other words, at the water heater, let's say we have 120. At the end of the pipe, we want to make sure end of the supply pipe is no colder than, say, 110. And we do it with a recirc pump. So what we're doing is under no load, under no flow, no load or no draw, we're trying to offset the heat loss in that pipe. So it's not a real big number because we insulate that pipe. And that hot water supply piping has to be insulated. It may be 200-300 feet long, but we insulate it. If you do the heat loss calculation, it's not that big a number. But we do want to calculate that number, and we do want to offset that loss so that at the end or the very furthest point of hot water supply piping, at a no-draw situation, that we have enough circulation to keep that water hot. How close? We're going to use 10 degrees a day, but you might use 20 in your designs or 5. It does not matter. The point is we're trying to make sure there's hot water available when you need it at the end of the pipe. So number two, We do not normally worry about the heat loss in the return piece of pipe. Notice you got a supply pipe that's insulated, you got a small piece of return for the circulator to recirc through. We don't normally worry about calculating the BTUs in that piece of pipe. We don't put it in our calculations. If you run a few numbers, and we're going to show you one example, we're not going to drill in it too deep, but what you're going to see is the actual BTU load here is pretty small. The actual BTUs per hour required to keep the supply pipe hot is not that many because it's insulated. It's insulated, so that's the point. So it's going to be very low GPMs. Translation, very small pumps most of the time. Very small pumps, and that's why we don't pay a lot of attention to it. We, in doing our calculations quickly, would normally assume the recirc line, the return line, would be equal to the supply line in length. It may not always be true, but if you're going to move quickly through this, most people just kind of make that assumption that the return length of pipe is the same as supply. Friction head for the pumps, what we're after here. So why do we want to take the time today to have you slow down? Just slow down and listen to me a little bit. Where are the potential recirculation problems? I said 90% of the time it's not a problem. So when do we need to stop and say, wait a minute, Edmondson said there might be a problem here. Under water heater temperature control, where you have instantaneous water heaters, you need to up the recirc rate to maintain control. So first place to look for is instantaneous water heater control, where you have small recirc pumps. You're going to have temperature control problems at low flow and low draws. And the way to handle that is to upsize your recirc pump. So in that case, we want to size it on some minimum flow, not on the heat loss. Second one would be unbalanced riser flows. If you got a high-rise building or you got a hotel or motel or school, not unusual to have direct return piping of the domestic hot water recirc loop. And when you do that, you got balance issues. And you're talking about 2, 3, 4, 5 GPM spread out through a whole building, and you're trying to balance it. So you got balance issues anytime you got direct return. In other words, you have to balance these things for them to work, or they will not work. Last but not least, and probably one of the most important ones that catches people off guard, in particular in high-rise buildings, do not recirc across a pressure-reducing valve. You're going to hear me preach that today a lot. Do not recirc across a pressure-reducing valve. You're going to have problems, and we'll define that for you. But those are the three major trouble points we want to make sure we get through. Obviously, the pumps have to be able to handle domestic water, and that's all we're trying to say in the bottom of the slide. So how do we get there? This is based on some research by Bell and Gossett, but basically, here's your sizing procedure. Determine the required flow rate to offset the heat loss, just like any other system you're working with. What is the BTU heat loss? How much do we need GPM-wise to offset it? What delta T you want to design to? What size is your recirculation return line? Is it going to be 3/4 inch, 1 inch? We got to know that return line so we can get the friction hit. Go to your Bell and Gossett system size or some friction chart, come up with your head loss for the pump, and select your pump based on flow and head. I repeat, very small pumps, as you will see very shortly. So let's take a typical apartment example, which is going to be very similar to what you see a lot. And let's go through this and show you the procedure. I'm not going to drill through every number. I just want you to understand the procedure. Once you got the procedure down, you begin to see why it's so small, and you know when and where to take a look. Then there's some shortcuts you can take based on the pipe length and the pipe size, and we'll give you a chart for that. By the way, Bell and Gossett has a TEH manual on domestic hot water recirc. If anybody that tunes in on this little presentation wants one, send us an email or go on the JMP website, contact us and send us a note. We'll be happy, free of charge, to send you a copy of the recirc manual. Basically, here we go with a typical fixture unit count for sizing pipe and coming up with demand and flow in GPM, which again, we're not going to spend an awful lot of time on, except you to note the bottom statement there. We're going to have 12 risers. They're going to be 25 feet apart for a total supply pipe length of 300 feet. Total supply pipe, domestic hot water supply pipe in the building is going to be 300 feet long. So here's a little snapshot, a little picture of this apartment with one water heater shown in blue, and the green is a supply pipe for the domestic hot water. And remember, each one of those takeoffs is 25 feet apart. So now we got some total flow rate in GPM that we're going to go to the fixture unit charts, and we're going to come up with the GPM to size the pipe. So we've already sized the pipe for you. It's 2.5 inch in the first section, and you see each section it goes down a little bit all the way down to the very end where it's 1.25 inches. Then we tie in a little red piece of pipe is the hot water recirc line that we're going to draw water through back to the water heater to offset the heat loss in that supply piece of pipe at 300 feet. And in our example, we're going to hold it to 10 degrees delta T. So we're going to come up with the heat loss in BTUs per hour, and we're going to come up with the GPM required to hold that to a 10-degree drop. That's all we're trying to do, to keep that hot water hot. Because out at the very end, at riser number 12, if you go to take a shower, we want hot water sitting there for you even at 2 a.m. at night, ready to go, so you don't waste a lot of water. So as you start thinking about wasting this water thing a little bit, think about the fixtures, think about the runouts from the main to the fixture. How long should that runout be on riser number 12 from where we recirc it, where the green is, to where your shower head is? Is that going to be 10 feet, 50 feet, 100 feet? How long should we allow that to be? We'll keep talking about it as we go. So first thing let's talk about the heat load. So we want the heat loss in that supply piece of pipe. It's a little formula you guys are all familiar with. Q is equal to GPM times 500 times delta T. First question is, what is a good design delta T? I'm going to use 10. 20 would probably work. 5's okay, but I'm going to use 10 degrees, and I think that's very reasonable. A lot of designers use 10, but there's nothing cast in stone about that. So let's go to a little example and see what we got. So this is that very last riser out there, and I want to make sure you don't lose track of what we're doing here. If you look at point A, the recirc part is the green part of the pipe. That's where we're going to recircle water through. We're going to keep that hot. We're going to make sure that's within 10 degrees of the design supply hot water temperature as a minimum. But from point A out to point E, you've got to run out to the fixture, to the shower, to the sink, to the dishwasher, whatever it is. And we got to run out there, and that's going to be full of cold water when you first open your faucet up. So how long is it going to take you to get cold water, and how much of that water is going down the drain? That's the issue. So codes will define for you how long to make A to E without recirc. Another thing you could do between A and E is wrap it in heat tracing tape to keep it hot all the time. But there are codes that says to you how close to the fixture you have to recirc the water to keep it warm. There are codes that say to you the runout from E to A is limited so many feet. The old code in 2010 in most states out of ICC, International Plumbing Code, used 100 feet. Bell and Gossett is recommending at least nothing over 50 feet. And the newer codes, 2012 version of IPC in some states have also adopted the 50 feet. So I think a reasonable design today would probably be 50 feet run out between A and E max. Remembering you're going to waste all that water down the drain. However, some states are shortening that 50 feet up. Some states are making you heat wrap the tape. The longer that piece of pipe, the more water you're going to waste. And I'm going to show you shortly the low flow fixtures make this more complicated. But get in your mind, the purpose of all of this is between A and E, you go to take a shower, you're dumping the water down the drain, and you're wasting water. And however long that piece of pipe is determines how much water you're going to waste, even with hot water recirculation. So let's look a little bit at what we got on hot water circulation and what they're recommending to you. This is the old IBC, ICC code that most states are still on. And the point of this one is it did say 100 feet between the point of recirculation and the fixture. The 2012 code is some states adopt that. Remember, states are slow getting there, show 50 feet. Your local plumbing code may show a different number, so you need to check your local plumbing code and go for good design. Good design might be 50 feet, but you need to verify that for your firm. I hope you understand the point. So low flow fixture units. this so-called energy green design guide from ASHRAE, and you see USGBC stamps on the front of it, is encouraging you to go to low flow rate units. Look at this public metering self-closing faucet, public metering self-closing faucet, kind of there in the middle, 0.25 gallons per metering cycle. These are these faucets that you go into a bathroom like at a big airport, and you put your hands underneath them, and it hits a little photocell, and it cuts on, and it gives you 1/4 gallon of water. Recently, I came in from a flight from overseas to a major airport in the country. It was early in the morning, 6 a.m., and I guess I must have been the very first person in this bathroom recently, because it took me 20 times with my hands back and forth cycling to get hot water to where I could wash my face with hot water. Now I wanted hot water. I want to wash my hands and face with hot water. 20 cycles to get it. What's the message? The message is these low flow fixtures are indeed low flow. So if you got that run out of 50 feet, may be too long on some of these things if you are not willing to wait for a while to get hot water. Simple little comment, but these codes are going to begin to come into play very quickly, and you need to be aware that you might get that kind of complaint of how long it takes to get hot water with these public metering self-closing faucets if you don't pay attention to the link from the domestic hot water research point to the fixture. You got to begin to get common sense in this. So here's a little quick example of what I just told you. If you had a 0.25 gallon per metering cycle faucet to work with, will you ever get hot water? This goes back to my little experience in the airport. If you do a routine calculation on that, you come up with about 0.35 feet per second flow in a 1/2-inch copper pipe, about 0.35 feet per second on a 1/4 gallon per metering cycle. Common problem is because this is very low flow, and you're cutting it on and off. So if you got shorter runs, say less than 50 feet would be nice, but if you don't have, if you are at 50 feet and you got electric heat tracing on the runouts, fine, but if you don't, you're going to be waiting a long time for water. In other words, at 0.35 feet per second, divide that into 50 feet. How long is it going to take you to get water? Divide the 0.35 into 50. What do you come up with? A couple minutes? Think about that. A couple minutes. And that's kind of where we're headed. We do have a product called AutoCirc. It's a pretty good solution to that. We'll show you a couple snapshots, and it's something you might want to think about. Here's a slide that may catch you off guard. ASHRAE has a new standard committee they're working on. It's not passed yet, and it's not out for publication yet, but it's been in public review a couple times. And they're trying to save water. And the interesting thing is you will find that ASHRAE, ASPE, AWWA, and USGBC are all involved in this. This is the new standard 191P that the Board of Directors has not passed, but it's coming. I wish there was some of you young kids in the audience. It's going to be a huge potential for plumbing coming forward in the future. It's going to be some big changes. If you got AWWA and all these people agreeing on a standard, you know it's not going to take long for it to become building code. And this is how to save hot water, how to save cold water, how to conserve water. The one little thing on hot water distribution I want you to see is, look at what's in red down there, that from the point of hot water recirculation or heat tracing tape, your choice, to the fixture, you cannot waste over 16 ounces of water when you turn it on. Think about that. Think about what I'm telling you. You can't waste over 16 ounces of water from you go in to take your shower. That's all the water going to let you go down the drain to meet this code. Oh, man, that's going to be a huge change. It's going to be, you can't run 50 feet anymore, guys, and you're going to have heat tracing tape, or you're going to have to recircuit right up to the fixture. That's the message I want you to understand. The world is changing. Be aware. Here's the little draft of some of this stuff. And the message to you should be the chairperson of this standard committee that has not passed yet. It's not passed, but it will be. It's going to come. Is an ASHRAE member. Vice chair is AWWA member. Another vice chair is ASPE. Another vice chair is USGBC. My point being is if those people agree on something, look out. It's going to happen. Here's another standard committee that I think you should be aware of. This Legionella thing. Yes, ASHRAE has a standing committee coming on Legionella. Has not passed the board of directors yet, but they're so serious about this, they've recently taken Tom Watson, who was last year's society president, and made him chair of this committee. It's that important to get it out and get it done. There are some issues with Legionella. Number one issue I told you about a little while back, this might be a little good news for you. They recognize that the Energy Code 90.1 telling you to circulator on and off, and OSHA telling you to run it continuously is a problem. So what they're trying to do is work through those conflicts that we got, but at the same time take care of the Legionella problem, which in essence is going to mean we're going to have to, somewhere in this flow loop, heat the water to 140 and kill this Legionella. That's what's going to happen. It's going to be a lot more complicated than that, but that's where we're headed. I wish I was a young kid working in the plumbing business. I'll give you kids a prediction. 5 to 10 years, every commercial building we deal with is going to have 2 plumbing systems in every commercial building. One is going to be reclaim, gray water, recycle water, rainwater, recollection. The other system is going to be potable water. So we're going to have 2 plumbing systems, one for potable drinking water and one for reclaim, recycling water, flush water, whatever you want to use it. We're going to break it down. Every system. It's just the beginning. And we're going to have low flow fixtures. Just think of what's coming. You guys need to be all over this because it's the future. Whether you like it or not, we're going to have to save water. With that out of the way, so you understand how important this is, I hope you kind of get the message. You need to learn all this. Let's look at a simple recirculation system. And this is the one we looked at a little while ago where we got 300 feet of pipe. Let's take a quick look at it. Now here's a little chart B&G put together. And you can do the math, but basically if you got a 10-degree drop, then at 10-degree drop, 1 GPM will allow you to get 5,000 BTUs. If you had a 20-degree drop, 1 GPM would allow you to get 10,000 BTUs. In other words, if my heat loss on a piece of pipe was 10,000 BTUs, I could flow 1 GPM through it at a 20-degree delta T. If my heat loss was 10,000 BTUs, I could put 2 GPM through it with a 10-degree drop. So the message is this is a way for quickly in a table way of calculating the GPM required to offset that heat loss in my supply pipe. Good. Then you send a little chart BG's prepared, and we really shouldn't pay attention to the non-insulated pipe. You can if you want to, but the first column is insulated copper tube or steel pipe. And notice that 4-inch piece of pipe, huge piece of pipe, supply pipe. It's only 5,000 BTUs per 100 feet. And you see from the previous chart how low a flow rate that would be. And a 4-inch supply pipe, ladies and gentlemen, is huge. It's a huge piece of pipe. So you're beginning to see this heat loss when you got insulated supply pipe for domestic hot water. It's not a real big number. And that's the message we want to give to you. Now, we don't have the time today to sit through and take off every piece of pipe in that 300 feet of pipe I just showed you. But B&G has done that, has taken it off by pipe size, by the length of pipe, and calculated the supply pipe heat loss. And it's 9,320 BTUs. In other words, between the water heater B all the way out to riser number 12, all that green pipe, we got a supply heat loss of 9,320 BTUs that we need to offset to keep that water hot so we don't waste it when you turn on the shower at riser number 12. So that's not a, and that's a 2.5-inch pipe is what we started off with. That's a pretty decent sized system. So if you decided we were going to start at 140, and that's probably hot, and you were going to hold 130 at the end of the green piece of pipe, that would be 10-degree drop. It takes 1 GPM per 5,000 BTUs. 1 GPM per 5,000. I only need 1.87 GPM to offset those BTUs. So my pump, believe it or not, is less than 2 GPM. So we told you this is some very small numbers. Now, if I go to a 3/4-inch copper line on the red piece of pipe, the hot water return, then the friction at 2 GPM through that 3/4-inch piece of pipe is 1.4 feet per 100 feet of pipe from a Ballingosset system size. So I add all that together and quickly putting a check valve, a supply pipe we don't even worry about because it's huge, only flowing 2 GPM. I'm not worried about the water heater with 2 GPM. My total friction loss for my pump is 5.2 feet. Make a long story short, you've got to go pick a pump for 2 GPM at 5 feet ahead after all those calculations. So that's just why 90% of the time we don't do this. It takes time. So, by the way, we base this on 140-degree supply heat in the supply piece of pipe with an ambient temperature of 70. If you have colder ambient or colder supply water, this is a little formula that you'd offset it. In this particular case, we've dropped it to 120. As you can see, the BTU heat loss is much, much less. So the message is this is conservative at 140, little chart we showed you. So let's go back to our example. 300 feet of supply pipe. I want to make sure it starts at 140 at the B, and at fixture 12 I'm at 130. And again, I repeat, it would probably be more like 120 to 110, or maybe 115 to 105 would probably be your actual numbers. But we're looking at 10-degree delta T is what we're looking at. It takes 2 GPM to do that at a 10-degree delta T. Now, here's another little chart that B&G put together. And this is insulated pipe at the top. Don't worry about the bottom. The red's insulated piece of pipe. On the right-hand side are 2 very common B&G pumps, little NBF 25 or the old Series 100 all bronze that some people still love. But the little NBF is the wet rotor bronze pump that does the same thing as the 100 does. But what you need to get out of this is, if I had an 1.5-inch pipe and it was 800 to 1,200 feet long and it was insulated, I got an NBF 25. Listen to me now. Listen to me. If I got a 1/2-inch recirc line and my supply pipe's 200 feet long, I got an NBF 25. So what you guys have done is you put NBF 25s on everything, which is fine. And it works 90% of the time. That's a pretty big changes in pipe supply. So what you have learned over the years is 90% of the time, this recirc thing is not an issue. Let's just throw an NBF 25 on there. We'll be fine. And that's normally true. So when is it not true is a reason for this seminar. By the way, I mentioned to you some new technology, and B&G has it as an auto circ. We have some competitors with similar products. Well, we do not have a hot water return line. This particular case is under the fixture, the last fixture out there. And you hook the cold water and the hot water to the little circulator. And what it does, and maybe the next picture helps show a little bit more, you see how this is the same auto circ out at the end of the pipe. And there's no domestic hot water recirc line. It's on the domestic supply line. Supply hot water, supply cold water. So what the circulator has done is they're connecting the hot and the cold water supply to that last fixture into the circulator. There's a temperature sensor in that little circulator. If that circulator senses the set point, 105, 110, it cuts off. If the temperature drops, and there's a little delta T there as well, just say 100 degrees, whatever your set point is, if it senses it, it turns on the circulator, pumps a little bit of hot water into the cold water supply side. A little bit of hot water into the cold water supply side until that temperature is back up to set point, which is what, 105, 110, whatever you got set on. It's very little water, cuts right back off. It's very little water, and it's not going to upset you because it's just a touch of hot water to the cold water side to maintain it. So when you go to that fixture to take a shower or wash your hands, you got hot water instantly. This also comes on a time clock. If you want to have a time situation, so you can time it at off hours or whatever you want to do it. But this is some new technology, kind of a point of usage, but it also will maintain hot water to all the fixtures going out there. So if you put one at the end, and it does away with the domestic hot water recirc pipe. Great idea for fixing problem jobs you may have. Here's another little snapshot showing showers and how it fits underneath the sink. You will need a power supply out at that last fixture to plug it in 110. And just some quick comments to take a look at. Here's a little picture of it. We're not here to talk product, but just you see how the top cap has a cold water supply and a hot water supply going into it. Very little energy usage on these things. In fact, we see a lot of them in houses where you don't have domestic hot water. Maybe somebody's upstairs 3 or 4 floors away and they're waiting a minute or two for hot water and then all that cold water is going down the drain. This will fix that problem nicely for you, very inexpensively. In fact, there's a newer version of it that's wireless, to where you put the pump at the water heater as shown. Pumps at the water heater, and there's a little valve out at that last sink that's wireless that senses the temperatures and turns the pump on and off to make sure that you've got hot water. It allows the hot water to go to the cold water side through a little valve, but it's all sensorless, so it works quite well. And look at the wattage, 14 watts. That's a night light. That's nothing more than a night light at my house. So interesting stuff coming that you guys should be aware of. Again, no hot water recirc lines is the benefit of this. Commercially and residential, great little application. So we got the wattage thing we talked about a little bit. Here's typical curves, but we're not here to really go through this, except this is really new technology you should be aware of. So quickly we'll move on and we'll go back to what are our problems with domestic hot water. Where should we slow down and recognize that that little 2 GPM pump at 5 or 6 feet ahead is going to get me in trouble? Where? Watch out. Watch out for water heater temperature control. Nothing beats a little storage. So anywhere you don't have any kind of storage, instantaneous water heaters of any type, be aware you may have supply temperature control issues if you don't over-recirc them, if you don't change your recirc ideas or have a little bit of storage. Either one works. 8.33 pounds of water in a gallon, so 8.33 BTUs is going to raise a gallon of water 1 degree, no matter what you do. And that's the issue. That's why a little bit of storage helps, or a little extra recirc helps. So basically, some publication, heating, piping, and application, air conditioning in 1985 by Gil Carson points this out. And in red is what I want you to read. And the punchline is this: we should increase our domestic hot water recirc pumps to 25% of peak load on these pumps to make sure we keep temperature control. Otherwise, when you cut on and off, your supply temperatures are going to change rapidly. You're going to have a hard time maintaining supply temperature control. So here's some comments on dead-end services with steam valves that we're just going to put here for you in case you have steam applications. What we find mostly probably gas-fired and electric. Instantaneous water heaters probably primarily gas-fired, but the same things happen with steam as well. So here's a typical example of a steam-fired instantaneous water heater. Could be gas-fired, does not matter, and why you need to recirc more water. So we are saying to you to take the peak load of the water heater and recirc, upsize your pump to 25%. So if this particular instantaneous water heater was 100 GPM, we're going to tell you to size your recirc pump on 25 GPM. Yet if you went back to the old way, it would only be 2. So you see, right now, we're asking you to take a different look at instantaneous water heaters and make sure you up the recirc flow rate to 25% of the peak load to maintain temperature control. The main thing you need to understand, top picture, that little green valve is a big old steam control valve. It's sized for 100 GPM, 40 to 140 through that water heater. And it's sensing temperature. It's sensing temperature, supply temperature to the building. It's not sensing GPM. It's not sensing load. It's only sensing temperature. So if you had one shower, this is a 100 GPM water heater, if you had one shower pulling in 1.5 GPM on the shower head maybe, and nobody else in the building, you got 1.5 GPM of the cold water coming in the black line, going through the black line, going to the supply, and you got a steam control valve that's maybe 4 inches, been sized for 100 GPM of cold water, and there's only 1.5 GPM there, and that water's cold. What's that steam control valve going to do? It's still sensing temperature, right? And it says it's cold. It's going to open wide open with 1.5 GPM of cold water is only load. So your load is what? 1.5%. Your load is 1.5%, and you're going to dump 100% capacity on it. So what do you think is going to happen in any instantaneous water heater if you actually have a load of 1 to 1.5 and that steam control valve is only sensing temperature and it's deaf, dumb, and blind, is the best way I do to describe it. It's going to open wide open, it's going to overshoot. So now you're going to have a supply water temperature running up to 180, 170 degrees going on that piece of pipe. So that's not desirable from scalding somebody having issues. And the only way to fix that is either storage or upping the flow rate of the return recirc pump. So B&G is recommending on all instantaneous water heater a minimum recirculation of 25%. Now, if we up to the 25%, think what happens. Now, that little 1.5 cold water supply coming in there is going to be mixing with a recirc pump bringing back warm water at 25 GPM. Go to your sensing point. Go to where your sensor is to this big old control valve. It's now sensing a mixture of 25 GPM of hot water, 1.5 GPM of cold water, so it's blended. So now it sees the actual temperature, and you could actually look at load a little bit better because now you've got a minimum flow rate of 25 GPM, not 1.5. And that's the whole issue. So how do you fix some of those things? Well, at the bottom, you see one idea. You're going to have a bigger recirc line for 25 GPM. So maybe you don't want to run a 2-inch piece of pipe all over your building. One thing you could do is go inside your equipment room, put a little bypass, and where you bypass it, put a circuit setter and set that recirc flow rate for 25 GPM, 25% through the recirc pump. But now your big pipe is only in the equipment room. Also makes a great place to put a little 100-gallon storage tank. I'm a big believer in a little bit of storage. I really am. I mean, you can't change that number I gave you. Is specific heat of water is 1 BTU, 1 degree per pound going to rise. So if I can have a little bit of storage, if I can increase that flow rate through instantaneous water heaters, so I have a better sense of where the real load is, I'm going to get a much smoother supply water temperature control, much better control of supply water temperature. And that's why on instantaneous water heaters, in summary, we recommend 25% recirc as a minimum. So we had to oversize the return line at 2-inch in this application, or we did a little bypass in the equipment room with the circuit setter and made it 2-inch, and now we got the recirc going through the 25%. We got good control now. Great way to fix problems. Watch out for unbalanced flows. And this is pretty simple. You got to bounce. Don't ignore this. Everybody thinks it's so simple. You have to bounce. So here we go with the equipment room with 1 water heater, 1 circulator, and this is like a hotel with a high-rise section, 7, 8 floors on one side of the hotel, on the other side of the hotel you got run out 1 level. How do you make that flow together? Here's your problem. Look at the recirc line length for going from riser number 12 back to the water heater versus the recirc line length coming in from the high rise. In other words, the red piece of recirc pipe is much longer than the blue piece of recirc pipe, just physically not the same distance. You got a little bitty pump. Remember, this is a 2-3 GPM pump normally. How are you going to balance that? And if you don't balance it, water's going to take the path of least resistance. So the high-rise portion is going to get pretty good water supply. It's going to keep pretty good hot water to the fixtures. The low-rise section out to riser 13, it's not going to get any hot water out there at low load, so you're going to have a big problem at night when there's very little draw. Bottom line is you got to put a circuit setter, you got to put an auto flow, you got to put some kind of lead-free device in there to make sure you balance it so you get flow on both sides. Just that simple. It's not a complicated statement. We did all the calculations here. I wish we had time, but we're back to GPM and head required each one. You're going to find the numbers are extremely low. 4 feet ahead one way, 5 feet ahead the other way. So very high, but very, very low head loss, very low flow rates, very small pump. We're back to that same pump. We're back to a Series 100 and EVF 25. And you're back to 2 GPM, 3 GPM at 5, 6 feet ahead. How are you going to balance it? You got to put circuit setters. You got to put flow limiters. You have to do some balance. In fact, you may have to upsize your circulate a little bit to make sure you got enough flow to balance. A circuit setter 1/2 inch at 0.25 GPM is impossible to read. So you got to keep that in mind. So let's take a little look as we go. We also recommend to go ahead and upsize your return pipe a little bit. If we make the return 3/4 inch minimum versus 1/2, we make it more self-balanced. We reduce the friction loss in the return piece of pipe. It makes it more inherently self-balancing because we've taken away a lot of the friction loss. So we just recommended that we make that return line, that red line, we recommended make sure we go to 3/4 inch, and that would make it more self-balanced. So what a couple comments. Anywhere you got multiple recirculation from different fixtures or different areas of the building, you're going to have to balance to get hot water to the fixtures. And if you don't, you're going to have big issues. In summary, we would recommend you really like to see you use 3/4 inch return. Can you make a half work? Sure you can. But we would prefer to see you use 3/4. It just solves a lot of problems that you're never going to have if you just go ahead and standardize that your minimum return line size is a 3/4 inch. You're going to solve a lot of your problems. So watch out for unbalanced riser flows. We talked about this. We want to make sure we do use the lead-free stuff. All the B&G circuit setters, just for the record, are lead-free. Feel free to use them on plumbing. They work great. You must balance. So here's a little hotel at World's Fair, and we're keeping it real simple. In 1983-84 out in Knoxville, Tennessee, and I was personally involved. And which free hotel room did they give me to go out and help fix this? I couldn't get a hotel room, make a long story short. And the owner said, if you'll come fix this, Chris, I'll give you a free room. Now, the problem was the brand new hotel, people were complaining they couldn't get hot water in the morning. In other words, after everything had been off any length of time, you go take a shower, it would take you forever to get hot water in certain sections of the hotel. Not the whole hotel. Certain pieces of the hotel could not get hot water. First thing in the morning would take minutes and minutes, 5-10 minutes, and people would just get irritated. So here's a piping chart for that. So you see we got risers, got a water heater on the right-hand side, a recirc pump. It's been sized, a recirc pump's plenty big, no big deal. Recirc line, but I hope you quickly realize there's no balancing valves. There's no balancing valves at the top where the little red recirc lines tie in. And this is direct return piping. By the way, I think it's kind of good for you young designers to kind of understand this recirc pump really is a closed system calculation, because really the only time the recirc pump really comes into play to solve your problems is when you have no draw. Now, as soon as somebody takes a shower, obviously plumbing is an open system. But the recirc pumps really come into play, they really do their job when nobody's taking any water out and you're just trying to keep everything hot. And by the definition recirc, we're going around and around and around. So it's really kind of a closed system head loss calculation. But again, you got a direct return set of piping here. You see that first riser? Where do you think that recirc pump's going to flow if there's no balance? It's going to go through that very first riser, number 1. That's where all the water's going to be. So sure enough, as you moved out to the left to riser 3, 4, 5, and 6, the people on a riser 6 in the morning time could not get hot water. It took a long, long time. The poor old person on riser 6 in room M at the top, he or she was the last person in the hotel to get hot water. So that's my free hotel room. So they gave me my free hotel room at the very top of riser 6. And the owner said, Chris, free hotel room, but you got to take a shower at 2:30 in the morning. And you kind of laugh, but you see the point. The point was he knew where the problem was. He didn't know why he wanted it fixed. So how would you fix the problem? Pretty simple. And I click back and through, back and forth again. I just added circuit setters to the top of the riser. See what I did? But the problem now is I even put a circuit setter on riser number 6. Maybe didn't need it, but I put them on every riser manually. Now, the problem I got now, the flow rate's 0.2, 0.3 GPM. It's kind of hard to read. But really, the simple thing to do here, the way we did this, we put our hands on the recirc pipe. We started throttling back at riser 1, 2, 3, 4, 5, and 6 until number 6 riser. That would always be wide open now. The circuit setter there would always be wide open. Until I felt some warmth with my hands, just that simple. Until we got hot water there at night. With everything off, I had hot water flowing through that piece of pipe. And then we gradually changed the setting on all of them to every riser at night had hot water touched to your hand going through. That's how we did it. We couldn't read the circuit setters, but that worked fine. Put our hands on it, worked like a champ. And that's how we solved the problem. It's working fine today. So lead-free circuit setters are required. Just kind of keep that in mind. Circuit setters will work fine, but you're probably going to have to do a hand reading. You're probably not going to be able to put a readout kit on and actually read the flow. You might want to go to an autoflow type of balancing device or some flow limiter. Autoflow makes them down NSF lead-free, I think 0.3 or 0.4 GPM that you can order from the factory. But if you do that, then what would you have to do here? 1, 2, you got what, 6 risers. You have to make sure you oversize your recirc pump to pump about 3 GPM to make sure you got enough flow rate so each one of those things will work. I see a lot of engineers doing that they're putting flow limiters in each riser and taking that minimum flow rate to make that flow work, and they're oversizing their recirc pump to make sure they got enough flow to make it work. So making it self-balanced. And making them self-balanced with a little flow limiter makes a lot of sense. So let's keep looking for the next possibility. We know about the lead-free thing. I won't waste a lot of time. I think you know everybody's got to go that way. It is just a matter of code. Excuse me. The B&G circuit setters, as I mentioned, are NSF. No big deal. Use them on plumbing. And we talked about typical risers coming back and forth, up and down. Basically, you want a check valve coming out of each one. Where your red return line is coming, we want to make sure on the return side you have a check valve. So if your pressures get out of whack, you don't get reverse flow through the return line. You don't get reverse flow through the return line. So simple little comment, little check valves coming out of domestic hot water recirc lines in every case, however they tie in. I mentioned to you to watch out for hot water recirc pumps across pressure reducing valves. I've said to you, never do it. I can't scream in this, I'll blow your brains out. But if you were in one of my seminars, I'd be pounding the table right now because I see so many people make this mistake. On a high-rise building, do not take a domestic hot water recirc pump and try to recirculate it across pressure zones, across pressure reducing valves. It will be a problem. So we're back to the World's Fair again, 1983. Same owner, Chris Edmondson, coming to Knoxville again. And I got a phone call, a different hotel. This was a high-rise. And they were complaining about, again, that cold in the morning that a person going to take a shower in certain parts of their hotel couldn't get any hot water. It would take forever to get it. And it's the same owner, same contractor. We fixed the previous one. He says, Chris, if you come back out here, I'll give you another free hotel room in my brand new high-rise Hilton Hotel downtown Knoxville if you try to help me fix this problem. So here I go. I sold the equipment. I'm making friends with a contractor. Why not? So here's a picture of that high-rise Hilton Hotel. The chain, I think the name has been changed to Quality now, but the hotel's still there. It's roughly 20 stories tall, downtown Knoxville. And I want the exact height, but I think that was it. And here's the pipe layout. We got one water heater. The pressure coming in from the pressure boost is 120 pounds. That's the green. Goes through this water heater, heats the water up for the whole building, rises up to about the 10th floor, which is about 100 feet up, and we're at 70 pounds now, and we go through a pressure reducing valve. We drop from 70 pounds down to 50, and then the hot water is fed down from that 10th floor, starting at 20 back down to the bottom at 70 pounds to all the rooms to keep the pressure below 80. Remember, by building code, you can't be over 80 pounds to a fixture. In fact, 80 pounds, in my humble opinion, you don't want to take a shower. You want the water pressure a little bit less than that. 80 pounds is a pretty hot shower. So in this case, we're trying to hold the pressure to a max of 70 pounds on any fixture. So then on the 10th floor, we kept on going up to the 20th floor, at which time we had a down feed again, and we downfed all the pressures there from 20 back down to 70. So that pressure reducing valve, I hope you recognize on the 10th floor is the problem. Let's see how it's the problem. We got one recirc pump coming from the top, the red, coming from the D 20 pounds pressure coming down to the very bottom floor, and there we're tying in with the recirc line from the bottom 10 floors to a little B100. There's my little 2 GPM in NRF or in B100 bronze circulator again. Same circulator is fine. The heat loss is nothing. Heat loss is nothing here. Back to the water heat. So where's the problem? The top 10 floors work fine. The bottom 10 floors, I hope you recognize, is a problem because we got a recirc pump trying to cross that pressure reducing valve that we dropped 50 pounds in. So let's see where the real problem is. Do you see where the 70 pounds blue is? Going through a check valve into the red. So you telling me that 70 pounds will not flow into 118? No, I don't think it will. I don't think that recirc pump of 70 pounds is going to flow into the 118 down to the recirc pump. So the top 10 floors are recirculating nicely. The top 10 floors are happy. Everybody's got hot water. The bottom 10 floors, they cannot get hot water on a cold day, it's just about impossible to get it there. You get it there, but you're going to have to flow a lot of water down the drain. Before you get water, you got a lot of mad people having to wait that long to get hot water to a shower. So you see the problem again, hopefully, as we cross that pressure reducing valve. And I hope you see from a physical engineering standpoint that 70 pounds of pressure is not going to flow in the 118. So how would you fix the problem? We've got to fix it quickly. So as you see here, I'm just changing back and forth between the slides so you understand the point. You see where the problem is there. I'm going to add a circuit setter or a balancing valve on that return line coming from the top 10 floors. I'm going to take a huge pressure drop across. I'm going to take 52 pounds. And when I take that 52 pounds of drop, I now have the 68 pounds red, where before it was 118. I'm down to 68 now. So now my blue recirc line will flow into my little red recirc line there if that pressure is that low. So everybody see how we can make it? We balanced it. But what a huge penalty in energy cost, what a huge penalty in a pressure drop to make it work. This is how we made it work. Then we take the return line down to the recirc pump. But wait a minute, now my recirc pump has a suction pressure of 68. It's got to get into a water heater at 120 pounds. And that's the problem. So how are we going to do that? Well, my little NRF22 ain't going to work anymore, right? I'm going to have a low flow, high head pump. I got to have a low flow, high head pump. In this case, we actually took two inline series 60s, 2 horsepower each, and put them in series. Put 2 pumps in series, 4 horsepower total, two pumps, 2 horsepower each, to give me a pump head of 122 feet at 6 GPM to make this thing work. We made it work. But why so much head? Remember, we're forcing the thing to work. This is not good design, but we're forcing it to work this way. That 122 feet of head, ladies and gentlemen, has to be there to offset what? To offset the pressure drop in the pressure reducing valve. Remember that PRV valve, we dropped 50 pounds through it? We got to put the head back somewhere or it's not going to flow. So we had to make sure we had enough head to offset that. So the problem is we've got a recirc pump trying to recirculate across the pressure reducing valve, and that's going to be an issue. You're going to have to put a very high head, low flow pump in there, or you're going to have to design it differently to make it work. So in summary, here's another little snapshot of the problem. And you see that PRV valve up there, and we're trying to recirc across a PRV valve, and that's trouble. You can make it work with a very high head, low flow pump, which is going to be an energy hog. We can force it to work, but I think there's a better way to get there. So maybe a good solution, which all high-rise buildings do in some form or fashion, is 2 water heaters. It's 2 recirc pumps, 2 pressure zones with cold water going to makeup, and you got a pressure reducing valve, but that pressure reducing valve is on all the water before it gets there. So that pressure reducing valve is reducing the pressure to the low zone, and I got a low level water heater for the bottom 10 floors with the recirc pump going around and around and around, and notice it does not flow across the PRV. Notice it does not flow across the pressure reducing valve. Now I've got a high level water heater and another recirc pump for the top 10 floors. And as you see, it goes through that water heater to the top, all the way back down, round and around, and that second recirc pump never crosses a pressure reducing valve. And that's how all high-rise buildings are done, and I think you see that kind of solves the problem. So here's another good selection, without going too detailed on all this. Different pressure zones for every 7 to 8 stories is what you're going to wind up with. That's what you got to do. What's the moral to the story? Never have a recirc pump cross a pressure reducing valve. If you're going to do that, you're going to have to add the pressure drop back across that pressure reducing valve into your recirc pump. And in my case, I just showed you I had to have 122 feet ahead on a 6 GPM pump to make it work. So just typical examples of high-rise buildings that we will not take our time to go through every one of them, but these are typical examples of how you make it work with recirc pumps. And here's a good job in Charlotte the same way, but you see the pressure reducing valves, particular job in Charlotte. The very bottom, you see a water heater and a recirc pump. It does not cross the pressure reducing valve. The pressure reducing valve reduces the water pressure to that zone, to that pressure zone. That pressure zone has a little water heater and it goes around and around and around. Another example of one with a brazed plate heat exchanger. And you know what a brazed plate is instead of a water heater. And it shows a piping diagram on that one as well. And then we see one with multiple pressure boosters, one for cold and one for hot, another approach. But what we see in most situations, this last picture I want to show you, this is a typical high-rise building. And what I want to get across, this is a very, very high-rise building. Your max pressure to a fixture is 80 pounds. You probably don't want to put that to a shower. Your minimum pressure to make a water tank work is, what, 20 pounds? To make a flush valve work, what, 25 or 30 pounds? So you're hung in a high-rise building between 25 and 30 pounds to a max of 80 pounds on any fixture. So what they do in a high-rise building is they create pressure zones. Every 6, 7, 8 stories, they have a different pressure zone all the way to the top. And there's several different ways to get there, but most people will put a water heater for every 6, 7, 8 floors with a pressure-reducing valve and a separate recirc pump for each pressure zone, so you don't recirc across a PRV valve. If you're not going to do that, then your recirc pump has to be high head, low flow, to force recirculation across a pressure-reducing valve. More to the story is, if you're doing a high-rise building over 6, 7, 8 floors, remember this seminar. Remember talking about it. Slow down. Remember that slogan. Never let domestic hot water go recirculate across the pressure-reducing valve and stay out of trouble. This is one of the biggest pitfalls we see, and the primary reason is most designers don't deal with high-rise buildings that often, so it kind of catches them off guard. Have a great day. This is the end of the seminar.